Greetings. This is Divam Trivedi pursuing Masters in Robotics at WPI University. Today I'm gonna discuss about a research paper titled Robust Shared Autonomy for Mobile Manipulation with Continuous Scene Monitoring. The autonomous degree of a robot is directly linked to the predictability in the task and environment that it works upon. In predictable environments such as factories, robots work fully autonomously. However, in less predictable and variable environments such as in fields or construction sites, teleoperation is the way to go, with humans working as the decision makers whereas robots work as the extensions. Many industrial applications require high concentration, manual dexterity, and scene monitoring, hazard detection, and prevention. Human operators are thus prone to fatigue, which has caused many serious accidents over the past years in many different fields. In this paper, the main focus is upon the robot bimanual mobile manipulator, which performs shared task space such as segmentation of objects and automatic mobile placement and navigation to place the objects that is desired into a bin. This robot adapts to dynamic changes, including changing object and target locations, and also monitors scene to facilitate safe avoidance and replanning of the motion. Key challenges to autonomous operation in variable and unstructured real-world environments include, first of all, perception challenges. There is difficulty in segmenting objects and thus recognizing the target object, since we have less than three-dimension object available due to the misalignments, occlusions, and robot geometry. The next on the list will be the motion planning challenges, which results in the issue from synthesizing collision-free motion that handles robot redundancy and real sensor data, which requires robust and adaptive planning. There are also several computational limitations in the real-world scenarios, such as onboard computing power, lower amount of memory, and online planning capabilities. This leads to trade-offs between algorithm quality and execution speed. This paper focuses upon multiple parts, such as first being the robust model-free affordance segmentation, which incorporates dense virtual representation of the 3D map in the surroundings that creates a representation of that 3D scenario of the workspace that increases the robustness of the model. The other will be the collision-free motion planning that integrates scalable and robust collision-free motion planning using a hybrid scene representation. The paper also talks about environmental awareness and adaptation of the robot that does so by adding continuous scene monitoring and failure recovery options for safe operation in workspaces. Over here, we have the system architecture. There you can see we have the shared autonomy that passes the feedback into the mapping and the scene interpreting. Once the scene is monitored, the endpost selector is chosen, which ensures that the gripper or the end effector of the robot tends to go to the position of the target. After this, navigation takes place, which actively detects the change in environment. This leads to motion planning and thus execution of the trajectory that also results in continuous collision avoidance of the robot and thus reaching its target. This is all done using extensions that is required to apply this framework to any mobile robot. In this paper, they have considered RGBD sensors, stereo cameras, LiDAR sensor, as well as a mobile base, along with two industrial manipulators, in this case UR5 by Universal Robotics. Going into a little bit deeper into the system architecture, we'll see a couple of parts which are the main frame of this particular paper. The first being the perception. In order to reduce artifacts which hinder the reliability of motion planning and object segmentation algorithms, raw RGBD and block match stereo sensor camera data is filtered in a pre-processing step that removes the self-observations, occlusions, shadow points, along with noise. Thus, using multiple cameras and sensors, multiple point cloud sources can be adjoined and fused. The pre-processing pipeline is as shown in the diagram on the below left side, where on the green part of it and the color RGB part of the camera can be seen as the dense and visual map for the segmentation. Whereas on the right we can see the octo map for planning, which is on the right side, in which we can see the robot as well as the target and the environment. The second important part of this paper relies on continuous scene monitoring, which gives it environmental awareness. The Octomap server generates a 3D occupancy grid map for obstacle avoidance, and scene monitoring integrates sensory data for environmental reasoning in variable and continuously changing environment. The motion planning and execution part takes place by the Exotica framework that handles motion planning and collision checking, which utilizes feedback from scene monitoring for efficient and safe trajectories. As we can see the KUKA LWR driver and controller is also used over here, and the entire workflow can be seen on the map flowchart on the bottom right. The system evaluation takes place in two stages, where the first experiment is the table clearance with the KUKA LWR arm. Starting with a dense visual map, a table surface and clusters, distinct point clusters are extracted and meshes fit via triangulation. Finally, primitive shape affordance are fit to the meshes and annotated with possible grasps, as we can see in the top three images on the left side, where all the three images are the three steps that takes place by the KUKA LWR arm, which is an initial evaluation phase that takes place to be implemented on the actual robot. The second experiment uses the actual robot, that is a ClearPath Husky, which uses autonomous scene clearance. The scene monitoring continuously integrates the fused and filtered sensor data in an Octomap and reasons about changes. Here, the human reaches into the robot workspace, crossing the planned trajectory, as you can see in the figure over here, figure on the bottom. The robot halts the execution, as can be seen over here, and thus make sure that the human or the object does not get any sort of harm. Over here on the middle picture, we can see that the navigation and recovery task with no line of sight, as the robot is over here and the target is over here, which does not have any line of sight, and restricted communication that relies on teleoperated as well as autonomous sequences. The results take place in also two parts, where scenario 1 takes place for single object, whereas the second scenario takes place for second objects. The time taken by individual steps during the experiments are mapped out on an image, where the different every method of the pipeline is being mapped into various different methods, such as segmentation, IDRM, navigation, and finally followed by execution, navigation of the plan, drop, and execute release. Finally, the plan to nominal, that is the target, is also done and executed, which finally tells us the final aim over here. As you can see, the operator input is shown over here in the red, and the autonomous behavior is shown in black over here. The gray indicates the cumulative experiment time up to the setup and the current setup, that is the time that is taken by the previous workload. Now, over here, as we can see, that the first scenario takes place everything and finishes the execution in around 75 seconds. Whereas in two objects, it takes around 115 seconds. This is a good observation, since we can rely on that parallel processing of the two objects together is more beneficial and more effective in the long run. The proposed shared autonomy system has been demonstrated to complete tasks with minimal high user input level, with operating autonomously for the majority of the execution. As we can see over here, the black marker is more than the red marker, which shows that autonomous steps are more than the teleoperation steps. It is able to deal with dynamic changes such as updates to the target, affordance, or bin location, as well as an obstacle or human entering its shared workspace by safely pausing or replanning and even resuming the motion execution. This concludes on a multiple phases, that is the robust shared autonomy system that incorporates dense visual mapping, collision-free motion planning, and environmental awareness for safe and adaptive execution. Motion planning has been enhanced by using the IDRM algorithm that selects optimal mobile-based positions for maximum manipulability and robustness. Future research directions can include continuous adaptation to environment changes, motion flow, and better predictive tracking. This also includes incorporating dynamic reachability maps with reduced memory requirements. Over here in this paper, the computer has been run on 20 Hz on CPU, which is suitable for mobile platforms with limited battery power. The base position selection improves autonomy and adaptability by maximizing manipulability that enables simultaneous object picking, as we saw over in the results section. The inverse reachability maps enable real-time and post queries and increased robustness, but require significant memory due to the size of the workspace and robot model. Thus, we can say that this methodology adapts to the system and can be useful for mobile robots that work in continuously changing scene environments, and which might or might not have any other occlusions or dynamic changes in the model or in the path. Thank you.